So let's start with flip-flop kinetics now, which is the number 37 in your slides. Usually, we said that according to the case that we know, which is the general case, CP versus time, that the absorption is faster, okay, than the elimination as a process, right? Which happens, this is a common case in kinetic, or we call it the general case, or the conventional case. So it's more common than the other case, which is exceptional. Okay, when this happens, which is the general case that we have, okay, Ka is larger than K. That's why the rate of absorption is usually faster than the rate of elimination. Okay, if Ka is faster, okay, than the elimination, it means the half-life of absorption is usually what? Lower or shorter than the half-life of elimination. Okay, so according to this, when we were doing the residual method, or when we doing K and Ka determination, this is for sure because it's two curved from two sides. This is a rectilinear and this will be semilog. According to this case, which is my common general case, okay, I will have the terminal phase to determine what? K. Let's say if we are talking about semilog, and the residual to determine Ka minus Ka over 2.303, which means that the terminal phase, which is the slowest process in the model or in the diagram, will be related to elimination, and the residual line will be related to absorption. This is what you already know from whatever we said earlier, right? If we have the, this is the conventional common case that is usually in the, generally what happens with a drug, okay? But what if we have the exception? In the exception, we have Ka less than K, okay, which means the half-life of absorption is longer than the half-life of elimination, which means that it's the opposite of this. That's why we call it flip-flop kinetic. Sorry. Okay, so accordingly, for sure, we have a situation for this exceptional case in which we some certain kind of formulation, such as controlled or sustained formulation, in which the rate of absorption start to be low or lower than what is usually in the general case, what we usually have in the general case. So accordingly, if we have the profile that we are talking about, concentration on a similar graph, versus time, and we have this, the terminal phase, still we call it terminal phase, which is usually in any profile, the terminal phase is related to the rate limiting step. Again, and here, because it's the slowest process, is what? Is absorption, according to this, right? Here, the slowest process is elimination. So it's the rate limiting step. So the absorption is the rate limiting step, right? So accordingly, the terminal phase, which is usually the rate limiting step, or represent the rate limiting step, in this case should be related to what? This is in flip-flop, should be related to absorption, and the residual line should be related to elimination because it's faster. Okay, again, accordingly, if we will take this, the slope of the linear regression of this will be what? Ka, and I can determine half-life of absorption from it, and from here I can use this slope to determine minus k over 2.303, and I can determine the half-life of elimination from it, which means it will be the opposite of whatever you know here as constant from the general case. It will be the opposite. Usually, unless we mention that it's flip-flop kinetic, it will be by default the common case in which the absorption is faster and the terminal phase is related to elimination. Okay, so if we go to the 39 slide, so if you go to your 39 slide, you'll find that we have two options, right? And we have log CB versus time. And if we are talking about okay, so it's just two examples in which here 0.7 over minus 1 and Ka equals 1.72 over minus 1. And flip-flop, this is the usual case. So the terminal phase is related to elimination, or we can determine the elimination rate constant and the residual absorption rate constant. But if we have flip-flop kinetic, this will be Ka. So this will be wrong. This will be Ka and it's equal to 0.7. And this will be equal to K, which is 1.7 over minus 1. The question is how I can determine experimentally that whatever that we have here is elimination and whatever we have here is absorption. In other words, how can I determine if I have flip-flop kinetics or not experimentally? We have different ways or different experimental work that we can do, but some of them relate to the formulation, so I can change in the formulation to determine, okay, if I change this in a formulation, I'm pretty sure that this will affect the absorption. So if this stays the same, but the steepness of it start to change, then okay, we are talking about a common case. This is one way, but again, you need to know some information about the kinetic of the drug to have this profile at the beginning. Or we can give the drug as what? As IV bolus. Okay, single dose. We know that if we take the drug as IV bolus, that the slope of this will be related to what? Elimination only. So you will have number here. Then I go and compare to this and this. If it's equal, the slope of the terminal phase, which is, let's say 0.7 here, it means that it's the common case that I have, and the terminal phase is the elimination. But if it was not equal to this and it was equal to that, then it's the flip-flop and the elimination is faster than the absorption. Okay, this is one way or two ways to determine if you are having flip-flop kinetic or not. Okay, the last point in this in this video, video recording, that we will talk about area under the curve, total area under the curve. Before we said, and when we were talking about IV bolus, then we said that we need to determine area under the curve from 0 until t last, right? Plus area under the curve from t last to infinity, right? This was determined by trapezoidal method, and this was determined by what? The integration from, if you still have it and it's a little bit significant from last to infinity of the CB at certain time. This is for IV bolus, right? This is what we took earlier. The same will be for oral or extravascular single dose. Again, we are under the same condition, so we are talking about single dose and linear kinetic and extravascular and one compartment model. Okay, so we will do the same thing. Area under the curve equals area under the curve from 0 to last plus area under the curve from last to infinity. Okay, if we go again, you need to use direct linear if we are talking about linear determination using the trapezoids. This is for trapezoidal method. Okay, CB versus time. You will have this 2 diagrams, and you need to have the profile that is divided into as much as trapezoid as you can, so to make it more accurate, as we said before. The only until the end, which is your last. Okay, the only difference that you will have this as not trapezoid, or it will be your triangle. So we know that the triangle is half the height with the base, right? نص ضرب القاعدة ضرب الارتفاع. And or if you can just have it as half the bases, two bases. For the trapezoid, this is area of triangle, and this is area of a trapezoid. This will be the same because time equals 0, and concentration, the first concentration will be equal 0, so you'll still have the area of triangle. So you need to do whatever you want. So the sum of all trapezoids that you have, areas from 0 to last, and then we will have at the end, let's take this into a bit larger. So I have CB versus time. Again, I will have the end of it, okay, which is from last to infinity, right? And again, if you remember, this will be in your terminal phase, which is only related to elimination if we are talking about the common case in kinetic. Okay, so accordingly, this will be also, as you know, which is CB last over K, as we have only elimination phase only. Okay, so if you do the integration similar to whatever we have here, it will be CB last over K, which is the elimination rate constant, trapezoids, all the sum of all of them, to determine the area under the curve of it. And this will be the end of this, which was number 7. Okay, thank you.